Good afternoon.
Good afternoon, Malim.
You well?
I'm well. How about you?
I'm doing good.
That's
So,
great.
So you start off immediately. Our topic today is on hypothesis testing. Are you able to see my screen? And by definition, hypothesis, or when we are talking of hypothesis testing, a hypothesis is basically a claim.
Yes, I'm able to
Okay,
see.
fantastic. So we can start. I'm saying a hypothesis is a claim or an opinion about an issue or an item. And therefore, it has to be tested statistically in order to establish whether it's correct or not correct. So what we'll be doing is, given a statement or given some figures or some data, some statistics, we'll be able now to analyze and tell whether the statistics are true or they are otherwise. So whenever testing a hypothesis, one must fully understand two basic hypotheses to be tested. We have what we call the null hypothesis, and we have the alternative hypothesis. Once you understand these two, and it is very key because confusion leads to what we call the type 1 and type 2 errors. So when we are talking of the null hypothesis, this the hypothesis being tested is the belief that the characteristics that will be given are true. For example, let's say KEBS, Kenya Bureau of Standards, may walk to a sugar making company, let's say Mumia's Sugar, to try and confirm that the 2 kg bags of sugar produced are actually 2 kgs. There could be some challenges in the metrics or the weighing machines. Yeah. So they want to really confirm that whatever is packaged is 2 kgs and not less. So they'll conduct hypothesis testing, and the null hypothesis will be each kg or each bag of sugar weighs 2 kgs. So they'll want to confirm, or they'll be testing, that indeed each set bag is 2 kgs. Now, failure to meet the 2 kgs will now render them to the alternative hypothesis. So the testing is out to confirm that this is true. If it is not, we refute it. So what will be the alternative hypothesis? I've said our null hypothesis is each bag weighs 2 kgs. What will be the alternative? And we are repeating, this is statistics 1, actually. So when we are formulating a null hypothesis, we should also consider the fact that the belief might be found to be untrue, and therefore we are supposed to reject it. So we are supposed to formulate an alternative hypothesis which is a contradiction to the null hypothesis, or what we are purporting to be true. So when we reject the null hypothesis, we are going to accept the alternative. That's why we are calling it an alternative hypothesis. So alternative hypothesis of our null hypothesis, which is each bag weighs 2 kgs, will be each bag does not weigh 2 kg. So that once KEBS goes to Mumias and they weigh and they realize that the bags are not meeting the 2 kgs, we are going to accept our alternative hypothesis. So null hypothesis is symbolized as HO or H naught or H nil, H0. Yeah. So we have a H with a subscript 0 on the side. And then the the alternative hypothesis is H with a subscript 1. So as it is indicated here. Now, I've indicated that is very crucial while setting your null and alternative hypothesis, because at times, if you contradict, you may end up performing grave errors. Yeah? The reason why we are doing the hypothesis testing is to know what is acceptable and what is to be rejected. So all possible values which the test statistics will assume will be consistent with the null hypothesis, or what we are calling the acceptance region. If it is not, it will lead to what we are calling the rejection of the null hypothesis. And the rejected area is also known as the critical region. So the values which separate the rejection region from the acceptance region are called critical values. I think I have a diagram. Exactly, it's here. So we are talking about, so our null hypothesis will be the acceptance region. This is our H naught. Now I'm saying that what now separates the rejection zone, we have the rejected region. What we don't want is what we are calling the critical region. So this point here is what we are calling the critical region, or what we are calling the rejection region. So the values which separate the rejection region from the acceptance region is what we are calling the critical values. I've said that we got what we call the type 1 and the type 2 errors. So while testing the hypothesis, the null hypothesis, and deciding to either accept or reject the null hypothesis, there are 4 possible occurrences that might occur. The possible occurrence one is acceptance of a true hypothesis. So this will be the correct position, and this is what the statistician is looking for, accepting the correct decision. So when we accept the null hypothesis and it happens to be the correct decision, the statistics does not give absolute information. So the conclusion will be whatever you had been given is true. Are we there? Scenario 2 will be rejection of a false hypothesis. Now, when we reject the false hypothesis, it will also be a correct decision. If the sugar is weighed and it is indeed not meeting the 2 kg, then our alternative hypothesis will be true. So we are going to have the correct decision. Now, the third scenario will be rejection of a true hypothesis. So you can imagine, if you reject the true hypothesis, it will be an incorrect decision. So this is what we are calling the type 1 error. So type 1 error is when we reject a true hypothesis. Then scenario 4 will be accepting the false hypothesis. So when we accept the false hypothesis, it will also be an incorrect decision. And this is what we call the type 2 error. Now they are denoted by, when we are talking of the type 1, in probability, we normally use the alpha. The alpha, I think I have that information somewhere. Yeah, it's here. So we use alpha when it is type 1. We use beta when it is type 2. Then the other thing that I want us to remind ourselves is the level of significance. Now in statistics, in our previous class, we used the 1% level of confidence and 5% level of confidence. Remember, there is a question that you used the 30%, but the most common one are 1% and 5%. So a level of significance is the probability value which is used when conducting the test of hypothesis. and we have the steps. Of course, we reach to the step that accept or reject step number 5. So a level of significance is basically a probability of making an incorrect decision after the statistical testing has been done. So usually, such probability will use either 1 or 5%. So in our class today, we'll be using 1 or 5%. And by that we mean the provision of making the error is so small, we don't expect to make an error. So you can imagine if the manager makes an error when they are doing hypothesis testing. It means that whatever the activities that will be reported will be erroneous through and through. It is like doing financial statements and the figures that you are giving are not a true and fair view of the performance of the business, right? So this is an illustration of 1% level of confidence. So we are giving ourselves a margin of error of only 1%, right? And if it is 5%, if it is 5% level of confidence, we are giving ourselves a percentage error of accepting error up to 5%. Of course, these figures are interpreted and we go to the z-scores to get the actual figures. So if the standardized value of the mean is less than negative 1.65, we reject the null hypothesis and accept the alternative hypothesis. But if the standardized value, of course, is now more than the negative 1.65, we are going to accept our null hypothesis. And this is what we call the one-tailed test. So the graph that I've illustrated there is trying to show that, but you are coming to the example. So if the sample mean standardized value I'm saying is less than 1.65, and this is what we are illustrating here. If it is less than 1.65, we are going to accept all this region. Don't know what, so people are able to join. Don't know what is being prompting, what is prompting me to invite. I think it's just a system baggage. So we go on. So we accept if it is less than 1.65, in our case here, we are going to accept all this region. Yeah, so we are going to accept our null hypothesis and reject the alternative hypothesis because it means that all the figures will be lying on our rejection zone. So if the sample mean value is greater than 1.65, we are going to reject the null hypothesis and accept the alternative hypothesis. So the sketch is normally used for sample mean given greater than the population mean. When it is otherwise, we adopt this. So if the standardized value of the sample mean is between, now these are two-tailed tests where we have a region of accepting. If we are given a domain of data, or what we call the two-tailed test, we are supposed to choose or to tell whether our data is lying within the acceptable region. So for a normally distributed data, we expect that our data will be lying within the acceptable region. And this is for 5% confidence level. That's why we are talking between negative 0.495 and positive 0.495. When we are talking of the two-tailed test, this is normally used when the statistical work or there is a complaint that is lodged by either the customers or where we have given. Let's say, for example, we have indicated at our institution that our A is supposed to be between, let's say, 90 and 100. It means that any student who scores any marks 90, 91 all the way to 100 will have an A. There are cases where, let's say the student scores 88% and we give them an A. It will be a problem. So we are going to gauge, and this is normally found in especially if you go to a place like manufacturing industry, a place like DevKey, they'll be indicating if they are, let's say, processing the metallic rod, there is an acceptable limit of what the machine can process. That's why we are talking of the lower tolerance limit and the upper tolerance limit. If, for example, they are saying that the metallic bar is supposed to be lying between 15 centimeter and 17.5 centimeter, they have given themselves a margin of error of 2.5 centimeter. Therefore, it means if the customers are receiving these metallic radicals or the metallic bars and it is found to be exceeding 17.5 centimeter, there could be a complaint. So we are expecting that anything between 15 centimeter and our 17.5 centimeter will be accepted. So this will be our null hypothesis. So anything that falls below 15 centimeter or goes above 17.5 centimeter will be lying on the rejection zone. So this will be our alternative hypothesis. So alternative hypothesis is usually the rejected if the standardized value of the sample mean lies beyond the tolerance limit. So when we are talking of the two-tailed test, I've just given an illustration with the metal bars that are processed by DevKey. And I've said that they are giving yourself a length of between 15 and 17. If it goes outside that, you reject. It shows that there is an error in the manufacturing firm. When we are talking of the one-tailed test, this is a test where the alternative hypothesis is only concerned with only one tail of the distribution of the data that we are given. So if we are testing a business complaint, if the complaint is above the measurement of the item being shorter or being upper, and a good example is given there, a manufacturer of a given brand of bread may state that the average weight of the bread is 500 grams. The standard size of the bread nowadays is 400, right? But if a consumer takes a sample and weighs each of the pieces of the bread, and they tend to have a mean, an average of 450 grams, he will definitely complain about the bread which is underweight. Most customers will not complain when it is overweight. They normally complain when it is underweight. So the statistical analysis to be done will concentrate on the left tail. So our data will be skewed or will be looking at what is not meeting the 450 grams. Are you getting? And that's why we are calling it one tail. So the statistical analysis to be done will concentrate on whether our bread is meeting the 450 grams. If it is less than 500, it is statistically significant. So such a test will be referred to as one-tailed test. The reason why I'm giving all this stuff, when we are doing now the analysis of hypothesis, there is a step that you are supposed to indicate whether it is one-tailed or two-tailed. So on the other hand, the test may compulate or skew, this word compulate, or skew on the right hand tail of the normal distribution. So when we are talking of the right, on this side, just take this side. When we will be coming to kurtosis or skewness, they'll be telling you that this data, when they are skewing to the left, it is right. But for now, I want you to look at the data that is copulating towards the right. In other words, we are saying we are rejecting everything that is to the left. Are we there? So when this happens, the major complaint is likely to do with the oversized items that were bought. This will normally happen when you are buying clothes. Nowadays, people want to fit in the clothes what is really fitting them. So if it is baggy, they'll go back to the, and you know, some of these clothes, because of the errors in the production, it will be indicated that it is a size 14, kumbe it is a size 18. So we expect that when it is an oversize, customers are going to complain. Therefore, this test will be one-tailed. They are complaining because it is oversized, not because it is fitting them or overfitting them. It is because it is oversized, over and above what is the acceptable limit. Are we there? So this is how we interpret our error, and this is, I've just summarized this information from the Z-score. So when we are looking at the 5% level of significance, because we don't have tables here in the online class, we'll be talking of two-tailed test and we'll be using plus or minus 1.96. When it is one test, we'll be using negative or plus 1.65. When it is 1% level of confidence, for a two-tailed test, we normally use plus or minus 2.58. And when it is one-tailed, we use 2.33. Are we there? So let us start now doing the hypothesis testing. So whenever a business complaint comes up, there is a recommended procedure of conducting the statistical test. So the purpose of this test is to establish whether the complaint is valid or otherwise. And that's why we want to know whether it is a null hypothesis or alternative hypothesis for us to accept or reject, so that we do the correction. So these are some steps that are followed. The first thing is to do the statement. So we normally do the statement of the null hypothesis and the alternative hypothesis. Like in our case, we said that our null hypothesis is the bags of sugar to be 2 kg, is equal to 2 kg. If it is not equal to 2 kg, it is then our alternative hypothesis. Then from there, we get the statement of the level of significance. And you said we are going to use 1 or 5% level of confidence. Then from there, our third step is the statement about the test statistics. And here, what is to be tested? Is it a sample mean? Is it a sample proportion? Is it difference between means? Yeah, is it chi-square? Is it t-score? Is it z-score? Is it f-score? Yeah, so you'll be testing various parameters of statistics. And then step number 4 is to identify the type of the test. Is it one-tailed or two-tailed? So you can see where it is coming in. And then 5th, the statement on critical values. So from there, after knowing the type of the test that we are conducting, we need now the statement on the critical values using the appropriate levels of significance. And then from there, standardizing the test statistics. So we'll be talking of now the calculation to standardize, to know whether indeed or scientifically it is true or wrong, depending on the data that will be given. And then from there, we make a conclusion as statisticians. Yeah. So we can start. So in standard hypothesis test, in principle, we can test all manner, but I've said that we are going to concentrate on the statistics. We are going to concentrate. We can even go as far as the probability when you are using the Poisson. Yeah, but I don't want to go to that extent. So we'll be doing the sample statistics mean, proportion, and variance. And the related, we know the related parameters there are the t-scores. When do we use t-scores? When do we use t-scores? You got to answer me here. When do we use t-scores? Team, I remember giving this information in our previous class. That's why I'm candid. When do you use f-scores? And when do you use chi-square? Our statistics student is supposed to be knowing this. So when the sample size is so small, and we said our smaller sample size will be less than 30 out of the population, we normally use the t-scores. Yeah? So you'll be using the test statistics just as when constructing confidence intervals for small samples. When do you use f-scores? When do you use z-score? And these are the scores that you are supposed to be using to test the hypothesis. As a statistics student, you are supposed to understand this course. So Z-score is normally conversion of raw data to a standard score. And it is based on the population mean and population standard deviation. So when those two parameters come into play, we normally use Z-scores. So T-score is a conversion of raw data to the standard score. So when the conversion is based on the sample mean and the sample standard deviation, that's when we use the T-score. So I want you to differentiate between when we are talking of the sample and when we are talking of the population. So when the population data is not available, then we have to pick some sample data to compute. And that's when we get now to the Akina chi-square and the other distributions. Are we together? Therefore, I don't know what has happened. We go on, can start what brought us here. And I want us to start with, I want to give an illustration. We have an illustration here, illustration 1. And we see, or we follow the steps of now testing the hypothesis. So I want you to read it through. So I'm assuming we are through. So we've been given that illustration. We've been told that there is an NGO that needs to, or that carried a survey in the community where girls are married off. And the results indicated that the marriage age for the girls is 19 years. So in order to establish whether this is true or not, a sample of 50 women was interviewed, and the average age indicated that they got married at the age of 16. However, the different ages at which they were married differed with a standard deviation of 2.1. So if you add 2.1 to 16, you are going to have 18.1. Yeah, that's the standard deviation. Or if we subtract, we are going to get to some 13.9. Yeah. Now, the sample data indicate that the marital age is less than 19 years. Is this conclusion true or not? So we've been asked to test hypothesis. So conduct a statistical test to either support the above conclusion or to reject. Who will give us the null hypothesis for this data? This is a simple one. Who will try? Been told that the marriage age is less than 19 years. And we've been asked to use 5% significance level. Evelyn Duarte, help us set the null hypothesis. That's our step 1. Setting the null and the alternative hypothesis. Evelyn, can you hear me? Evelyn. I'll assume you are not in the class. Nicholas Moora. Nicholas. Lagat.
Yes, Mwalimu.
Help us set the null hypothesis.
Okay, let me try.
Yeah, give it a trial. We are waiting for you, Lagat.
Can I try it alone, Mwalimu kwanza?
How do you try it again? These are statements that you just give. Lagat.
Yes.
How do you try it again? We are in class. What are we testing? You see, the null hypothesis is what we are testing. You've been told to conduct a statistical test to either support the conclusion or not. What was the conclusion?
The sample data indicates that the marital age is less than 19 years.
So what will be our null hypothesis? Our null hypothesis is the mean marital age is equal to 19 years, isn't it?
Yes.
So that the alternative hypothesis will be, what will be the alternative? Now I've given the null hypothesis. The mean marital age is equal to 19 years. Victor Korir, 16. What do you mean by 16? Victor, you see 16 is just a number, isn't it? Support it. Jen Namu?
Can we talk of 16? Because we've been told that most of them were interviewed and the age indicated that they got married.
So the alternative hypothesis will be 16.
Yes, between 16 and 19.
Oh, no, 16 is the statistics, is the test statistics. I said the elephant in the room is trying to explain what is the alternative hypothesis. Did guys understand my example of, you see, when Kebs was going to Mumias, what were they going to do to Mumias? They wanted to establish that indeed it is a 2 kg package, isn't it?
Yes.
So any contrary information will be alternative, right? So in our case here, the NGO are alluding that the mean marital age is equal to 19 years. So the alternative hypothesis will be the mean marital age is less than 19 years. So because you've been given that the sample data indicate that the marriage age is less than 19 years. Let me tell you guys, you cannot say null hypothesis is equal to 19 years, then you talk of 16 years in the alternative. We must see 19. So you should be talking of either greater or less than, or not equal to. Are we together? But not equal to will come when we are talking of the two-tailed test. This is one-tailed test. Tuko pamoja?
Yes.
So that is our step number one. We have formulated our hypothesis. So null hypothesis is our mean marital age is equal to 19 years. If it is otherwise, we reject. And the alternative hypothesis is the mean marital age is less than 19 years because we've been given some sample statistics of 16 years, which is less than 19. Then step number two is the level of significance. We've been asked to use 5%. We don't have a problem with that. Then step number three is to test the statistics. In this case, we've already been given. In some data, you've just been given data to compute. But in our case here, we've been given that the test statistic is a sample mean age of 16 years. So this one is given, it is outright. What is the step number 4? To get the critical value. And you say that this is one-tailed test. One-tailed because the alternative hypothesis is an inequality. We are talking of less than. You said when it is equal or not equal to, that's when we talk of two-tailed. Whenever it is greater than or less than, or greater or equal to, we talk of one-tailed. So we are testing at 5% level of significance. So where does that place us? We said if it is one-tailed and we are testing at 5%, it is 1.65, isn't it?
Yes.
Yeah, so we are talking of 1.65. So be having this somewhere in your mind. After doing a lot of practicing, this will automatically stick. So when it is 5% level of confidence and it is one-tailed, we talk of 1.65. Because it is less than, I can even predict the answer. So we are talking of negative 1.65 because it is less than. If it was greater than 19, we'd be talking of positive 1.65. Are we there?
Yes.
So can we do that? How do you get the standard, how do you get the Z score for the sample mean? Sample mean. We did it in our previous class. So this is a formula. So the value of the sample mean, we said, it is the population, it is the sample mean population, we less the population mean. The sample mean, we less the population mean over the standard deviation. Yeah? So we've been given all the data. What is our sample mean? Our sample mean is 16. This is the sample mean, 16 years. Then the population mean is 19. So 16 minus 19 over the standard deviation is 2.1 years. How do you get the standard deviation of the sample mean? We said it is the standard deviation, small x, small s over the square root of the sample size. So we are talking of 2.1, 16 minus 19, all over 2.1 divided by square root of 50. Is it? If you look at our previous class, we had the test statistics for the sample mean. What are you getting? I'm just applying this formula. I've said 16 minus 19, that is my numerator. Yeah? Then my denominator will be, this is the formula for the standard deviation. It is the standard deviation, which is 2.1 over the square root of the sample size, which is 50. So we are talking of 16 minus 19 all over 2.1 divided by square root of 50. What do you get?
The answer is negative 10.
Negative 10.1. Yeah, negative 10.1 it is. So that's our answer. So are we accepting or rejecting? So we are saying negative 10.1, which is less than what you are testing was negative 1.65, isn't it? That's why we are talking of this rejection zone. Are you seeing my rejection zone? So anything that would have been above negative 1.65 would have been acceptable. So we'll give us a statement. So we are supposed to give a statement as our last step. So I want someone to start by saying, since negative 10.1 is less than 1.65, do we reject or accept the null hypothesis? The answer is even in the picture. Are we rejecting or accepting?
You're supposed to reject.
Yes, since our negative 10.1 is less than negative 1.65, we reject the null hypothesis. So by rejecting the null hypothesis, we are accepting the alternative hypothesis. Are we together? Yes. In other words, we are saying the marriage age in this community is significantly lower than 19 years, right?
Yes.
I want us to start to try example 2. We have an example 2 here. Kindly try example 2, following the steps that I've indicated. We've been told a foreign company manufactures electric bulbs, and it has assured its customers that the lifespan of the bulbs is 28 months within a standard deviation of 4 months. So recently, the company embarked on a quality improvement research for their product. After the research using new technology, a sample of 70 bulbs was tested, and they gave a mean lifespan of 30.2 months. Does this justify the research undertaken? Use 1% level of significance to conduct a statistic test in order to establish the truth about the above question. So our step number 1 is formulating the null hypothesis. When I'm marking these questions, I just look at how you have formulated your null hypothesis. I may end up giving you more marks in the formulation than in the calculation. If you are able to formulate the null hypothesis, I can easily tell that you know what you are doing. So I don't even waste time there. So who can help us formulate the null hypothesis? We'll go first. Nicholas?
With the null hypothesis, states that it predicts that the mean lifespan of the bulb is 28 months.
Wonderful. Yeah. So the mean lifespan of the bulb is 28 years. So what will be the alternative hypothesis?
The mean lifespan of the bulb is 32.2 months.
We tena umeanza kusema 32.2.
Sorry, 30.2 months.
Now you've told us that the mean lifespan of the bulb is 28, isn't it?
Yes.
So it cannot again be 30.2. It can only be greater or less than. You get?
Okay.
You've already hypothesized that the lifespan of the bulb is 28 months, isn't it?
Yes.
So what will be alternative? Now we've been told after research, the new technology shows that 70 bulbs was tested and they gave a mean lifespan of 30.2. What does this depict? It depicts that it's greater than, isn't it?
Yeah, greater than.
So our alternative hypothesis will be the mean lifespan of the bulb is greater than 28. Yes. Guys, I said, if you indicate a number in your null hypothesis, you cannot give an alternative hypothesis with a different number. You can only talk of greater than or less than. Tunaelewana? You have to use the same number because you are going to use that statement to prove otherwise. So if your statement is the lifespan of the bulb, the mean lifespan of the bulb is 28 months. The alternative hypothesis will be the mean lifespan of the bulb is greater than 28 because you've already been given a sample of 70 that tested 30.2. Tuko pamoja? Then step number 2 is the level of significance. Is it, the level of significance is 1%. That one is obvious, we are given. Now, is it one-tailed or two-tailed? It is one-tailed, so we are not comparing any data. We have only one test. Now we go to the test statistics. Our sample mean is 30.2, isn't it? So at 1% level of significance, what are we going to test? It is one-tailed and it is 1%. So that lands us at 2.33, isn't it? And because it is greater than, we'll be talking of rejection zone that is above 2.33. Just want to take you to the table. I said you are supposed to have this at the back of your mind. Don't even cram it. It's so automatic. For one-tailed test, it will be 2.33. And because it is greater than, we are talking of positive. If it was less than 28, we would have talked about negative 2.33. So we go on. I want you to test the statistics. So we are talking about this region. I don't know what is happening to my need for PDF. It's losing some of the diagrams. That's okay. So we are talking about this region. Yeah? So we'll be talking about the region from 2.33 or the 1% degree of confidence. So give me the standardized value. So our sample mean is 30.2 minus 28 all over 4 over square root of 70. Nelson Jenga, you are saying 13.9 or 19.1. Nelson, where are you coming from? Where are you getting these answers from? Nelson?
Malim, that was the previous question.
Oh, it was for the previous one. It's okay.
Yeah.
It's okay. So what are we getting? What are we getting as the answer? I already gave you a hint. The answer will be greater than 2.33. So if you are getting less than 2.33, forget about it. Should be more than 2.33. That's how you analyze. That's why I said, if you perform the hypothesis well, I'll just give you full marks because you'll get the correct answer. Bakari. Bakari Kibibi. Bakari, are you with us? John Owino. John, have you gotten the answer? Who has gotten the answer? Lagat? Guys, this simple calculation, you are supposed to have gotten it like, yes, I've given even we are talking of
0.601.
yes,
4.6016.
4.601.
The answer is 4.
Okay, 4.6. Someone can confirm this. So 4.6 is greater than 2.33. So what does this? What's the conclusion? Was the research justified? We've been told here, does this justify the research undertaken? Does it? Give me the answer using 4.6 and 2.33. That's where the answer is. So you are supposed to say, since 4.6 is greater than 2.33, we reject the null hypothesis. That's what you are testing, but accept the alternative hypothesis. We'll just say at one level, at 1% level of confidence, the new sample mean lifespan of the bulb is statistically higher or significantly higher than the population mean. In other words, we are trying to justify that the research was worthwhile. Are we together? Now that was for one-tailed test. Let's go to two-tailed. And for two-tailed is easier because we'll be talking of domain. Now, you've been given this example. This one is still one-tailed. You can take this at home. I think it is somewhere in the portal. I don't need to dwell so much on that. So we go to two-tailed, and this is normally for large samples. So a large sample is defined as one that contains more than 30 units. Yeah. So when n is the sample size, now the business or those who are constantly involved in looking at the standards or the specifications, they normally do the equality test and balances. And I've given an instance there to help us understand. In a business, those involved are constantly observant about the standard or specification of the item they sell. I gave an example of dev key. So trader may receive a batch of item at one time and another batch at a later time. And at the end, he may have concluded that the two samples are different in certain specification. For example, the weight is different. If it is about length, like I was giving an example of metal bars, if it is longer or if it is shorter, they might again need explanation. So it may become necessary to establish whether the observed differences are statistically significant or not. And that's why we are testing them at either 1% or 5%. If they go outside our provision, then it will be a significant figure. And that's why we are rejecting. So if the differences are statistically significant, then it means that such differences must be explained. Either there is wear and tear, or our machine is malfunctioning and it needs to be adjusted, or something else. We don't want to continue lying to the customer and they are not getting the value for their money or investment. So there are known causes, but if they are not statistically significant, then it means that the difference observed have no known causes and they are mainly due to chance. That's why in your business statistics 1, you had to study probability first before coming to hypothesis testing, so that you understand how probability and how the sample distributions are done before you come to the hypothesis testing. Now, let X1 and X2 be any samples whose sizes are N1 and N2 as the mean. We did this in our last class. So the standard when you are doing the estimations. So when the standard deviation is S1 and S2. So in order to test the difference between the two sample means, we apply the following formula. So this is our formula. Can you see it from your end? I said my Nitro PDF is not responding. I don't know.
It's not clear.
It's not clear, but we covered it in our last class. So it's like repetition. If you recall in our class for estimation. Well, I try to explain it. We are talking of the Z-score. Now, these are difference of two sample means. Yeah? So we are talking of our Z-score. This is Z is equal to, you can write it somewhere. Our Z is equal to the sample mean 1 minus sample mean 2. Sample mean 1 minus sample mean 2 all over the standard deviation of sample mean 1 minus the standard deviation of sample mean 2, where the difference now I've tried to explain the denominator. So our formula for denominator, if you go into our last class notes, we said that where we are getting the difference between the sample means X1 minus X2, you are supposed to be very keen. We know that standard deviation is given by standard deviation squared, no, square root of standard deviation squared over the square root of the sample size. Or we just talk of the, if you look at this, now this one you can see, isn't it? And you see this one, guys, the second one. What I've done, yes, I've just taken the square root over and above. If it was to affect the denominator, I would have said S, because if I now remove the square root from this one, My answer will be standard deviation over the square root of n. Are you getting? But I've squared everything to make it easier for you to understand. What you are supposed to know is, whereas this is negative, we are supposed to put a positive here. I remember emphasizing in my last class. So when you are getting the difference between sample means, although we are getting the difference here, we add. Do you remember? I said you remember this is an addition sign. Is it now clear?
Yes.
So we can go to the example. So we've been told that an agronomist was interested in a particular fertilizer yield output. He planted maize on 50 equal pieces of land, and the mean harvest obtained later was 60 bags per plot, with a standard deviation of 1.5 bags. So this is the first data, yeah? So we can easily tell that our N is 50. Our N1 is 50. Our S, or the standard deviation, is 60, right? No, our N is 50. Our S, and now the S, we have two S's here. So this is the S in the formula, is 60. Are we together? So this is the standard deviation squared. And then our S is 50. So we have 60 over 1.5 over the square root of 50. That is for the first part, because we are getting the difference in the means. We go on. So the crops grew under natural circumstances and conditions without the soil being treated with any fertilizer. That's the scenario 1. Scenario 2, the same agronomist carried out an alternative experiment where he picked 60 plots in the same area and planted the same plant of maize, but a fertilizer was applied on this plot. So in this case, we have fertilizer. So after the harvest, it was established that the mean harvest was 63 bags per plot with a standard deviation of 1.3. So we are in the second data. And in the second data, our standard deviation is now 1.3. So we are talking of 63 over 1.3 divided by 60. So I want us to formulate the hypothesis. Step number 1 will give us the null hypothesis. Now this one is easier because it is comparable. Will give us the null hypothesis. Try to observe the question. Give it a trial. Who will give it a trial? We are still shying away from making these things. It's good to try and fail than keeping quiet. If I was teaching you statistics 1, I would assume you don't know, but you covered hypothesis testing in your statistics 1. Did you, or you did not, or I'm assuming things here? What are we testing? We've been told conduct a statistical test in order to establish whether there was a significant difference between the mean harvest under the two types of field condition, one with fertilizer, the other one without. will give us the null hypothesis. The subtopic is differences between sample means. So a null hypothesis will be mean 1 is equals to mean 2. That's what we are hypothesizing. We want to know whether there is a difference between the first mean and the second mean. Just that. So what will be our alternative hypothesis? It is a two-tailed test. In other words, we are trying to tell whether mean 1 is equal to mean 2. If it is, our data will be lying in the normal distribution. If it is not, it will be lying on the rejected zone. Do you remember the sign for mu? Do you remember the sign for mu? The inverted U. Do you remember it? I'm trying to see whether, I don't know what is not happening to my data. I'm losing most of it. Let me try to stop sharing and I reshare. Yeah, I got it. So this will be my hypothesis. I have a problem with Nitro PDF. It's just copying stuff where it's not needed. So my critical values of the two-tailed test at 5% will be testing on whether my mean 1 is equal to mean 2. So this is my null hypothesis, this is my alternative hypothesis. Yeah. Step number 2 is just to know whether it is one or two-tailed test, and we know it is two-tailed. No, is to test the confidence level. Our confidence level is 5%, and 5% for two-tailed is 1.96. So remember the table I shared. So when you are talking of two-tailed and it's 5%, we are talking of 1.96. So don't forget about this table to give you a quick. Then from there, our third step is now to standardize or to get the difference now between the two means. Apply the formula for the difference between sample means, right? And in this formula, I've said that we've been given everything. Our mean 1, our sample mean 1 is 60. Our sample mean 2 is 63. So go with me, 60 minus 63. Then all over, under the denominator, you can decide to work separately, or you can just put it here. It's easier to work it separately. So all over 1.5 over 50, square root of 50, plus 1.3 over square root of 60. Or you put 1.5 squared over 50 plus 1.3 squared over 60, and then you put all over square root. Either way, I just remove my square root outside. I'm waiting for the answer. Now calculating the answer is not an issue. We just need to know where interpreting is now the key issue. You get the answer? If the data is not lying between negative 1.96 and positive 1.96, we reject it. But if it is within, we accept. For this one, you cannot predict. You have to go calculate. It's not like the greater or lesser than. This one you have to calculate. I'm waiting for the answer. What are you getting? Morphine. Morphine Odoyo. Morphine, are you in this class? Steve, today you are so quiet.
I'm around, sir.
What are you getting as the answer?
I'm still calculating.
Are you people using scientific calculators, or you are using the phone? Because a scientific calculator ought to have given you the answer like yesterday. Just need to play around with the brackets. I already have the answer myself. But it will be meaningless to give you the answer. That's why we are in class. Who is Oppo A57? If you don't indicate your name, how will I know who was in the class? You'll be marked absent when you are in. No answer yet?
Negative 7.89.
Negative 7.89, closer, but it's not the answer. Good trial. Ndumia. Ndumia. Olu has given us the answer. What is 60 minus 63? 60 minus 63 is 3. Just write that somewhere. That is our numerator. Just write it somewhere, we work separately. Then we go to the denominator. Our denominator we said we start with 1.3. Is it 1.3 or 1.5? Let me check. We start with 1.5. 1.5 squared, that is 2.25 over 50. Write that answer somewhere. It is 0.045. Then 1.3 squared divide by 60. You are going to get 0.028. Add the 2 and get the square root. So that will be 0.045 plus 0.028. So we are looking for the square root of 0.073. That gives us 0.27. So 3 divided by 0.27, what do we get? Our answer is 11.11. Are you getting that?
Yes, but so why is the answers different, but the formulas you said are the same?
So are you saying the answer is different?
My answer when I use the first formula, the one I take that 3 divided by 1.5 over the square root of 50. When I use that, I get negative 7.89.
Unless you have a problem with the reciprocal. Now, mathematically, that is correct. Now, okay, what you have right now, you know, the formula is supposed to be equal to the standard deviation over square root of n, isn't it?
Yes.
If I say is equal to standard deviation squared over n or over square root, I mean the same thing mathematically, isn't it?
Yes.
Yeah, you are supposed to get the same answer. There is no way you can get a different answer. The formula is correct, unless you have a problem with the computation. You can try it at your own time. Right?
Yes. Thank you.
So we have gotten our answer is negative 11.11. What does that mean? If you look at the formula has the absolute. That absolute is to mean we are spanning, the reason why I have this diagram here, we are spanning from the region between, let me see, from the region between 11, this is 11 point, if I have to indicate here, this is 11, negative 11.11 up to 11.11. Are we together? So we are talking of this region. So what does that mean? Is it outside or it is inside? Negative 11 is way too far. Positive 11 is way too far from 1.96. So we can say since 11.11, since negative 11.11 is less than negative 1.96, we reject the null hypothesis. Are we there? But accept the alternative hypothesis. So that means that the difference between the sample means or the sample harvest is statistically significant. So the fertilizer had a positive effect. You can even see that without even the computation. So that is how we are supposed to analyze the difference between sample means. I've posted a question in your portal for you to try this question. on the reading abilities. So you can go to the portal, you work from the portal. So I beg to end it at this point. I have 3 minutes for questions. Any question? So in absence of a question, if we go now to the proportion, you remember when you are doing the proportion. Now, the following method will still be used for the proportion. So you have the sample proportion. The formula is given by PQ over N. And we said that we evaluate our Q in form of P. So you know that statistically P plus Q is supposed to be equal to 1. So our Q is equal to 1 minus P. But I don't want to go there today. So what I want us to look for is that slight difference. So when you are talking of the Z score, we now take you can see my P, the proportion found in the sample, the actual proportion found in the sample. Then we less the hypothetical proportion that you've been given. And I want to show you an example. We've been told that a member of parliament claims that in his constituency, only 50% of the total youth population lacks university education. So a local media company wanted to ascertain that claim. Thus, they conducted a survey, taking a sample of 400 youths. Of these, 54 lacked a university education. And they want to test at 5% level of significance, whether the MP's claim is correct or wrong. You just need to identify what is what. So from the example, you can easily tell that it's a two-tailed test because we are having a hypothetical proportion that depicts that hypothetically, we are saying that 50% of all the youth in the constituency lack university education, isn't it? So our alternative hypothesis will be 50% of the youth do not have university education. So while equalizing, so we are talking of pi is equal to 50%, and pi is equal or not equal to 50%. And you've been given all the others are figures that we are inputting. So for this one, P and Q, it is 0.5. So if P is 0.5, Q will be 0.5. Because P plus Q is supposed to be equal to 1. That's the law of probability. So we are talking of 0.5 multiplied by 0.5 divided by 400. Our N is 400. So our sample size is SP and it is 400. So what's the answer?
Zero point 00625.
0.00625.
Yes.
Now we go to the Z. Now for the Z, we have our, you say the answer is 0 point? Come again, what's the answer? You are looking for the SP.
0.00625.
You've gotten 0.0625.
Zero 0.079.
0.079.
10, yeah.
So 0.079. So this will be our denominator, right? Our P is the probability, which is 0.54. The proportion found in the sample. You've been told it is 54%. This is 0.54. And the hypothetical proportion is 50. So 0.54, should write it here next to the formula. 0.54, oh, I'm losing. Can do it on your end. I'm losing 0.54 minus 0.5. That will be 0.04. Divide by what you've given us, 0.079. What are you getting?
It is 5. Sorry, sir. 25.
Yes? This is 25.
0. Yeah, 25.
0.025. That way.
Yes.
Okay. So we are talking of 0.54 minus 0.5 over 0.025. What do we get as the answer?
1.6.
1.6.
Yes.
Yeah.
It is a two-tailed test, and you are
1.6.
testing at the level of significance of 5. 5% level of significance for two-tailed tests is 1.96, isn't it? We go to our table. Should be 1.96. So that's what we are comparing with the answer. So here we are. It is 5%. It is a two-tailed test. So what does that depict? We've gotten 1.6. 1.6 is less than 1.96, isn't it? So we accept the null hypothesis. So the MP claim is accurate. Is it? Yeah, from the argument, we accept the null hypothesis. So the MP claim is correct. We are testing whether it is wrong. So the MP claim is correct because 1.6 is less than 1.96. Any question? Kindly do a lot of practices. Kindly do a lot of practice on this. If you go to the course outline, I've given there the books that we are supposed to be guiding this particular unit, statistics 2. So you'll be looking at the differences between other proportions in our next class. Enjoy your Friday and weekend.
Thank you.